Our next speaker is Dr. Sudesh Kaur Khanduja. Now we move to plant biology to mathematics. That's certainly a big jump. Her current interest is research in algebra and algebraic number theory. She is there at IISER Mohali.
Good evening, dear friends. At the outset, I would like to thank the President, Professor Raghavan Vardarajan, for giving me an opportunity to speak to such a distinguished gathering, and also to visit this institute situated in beautiful location. I would also like to thank our academy secretaries, Madam Gati Hassan and Professor Gopal, along with the executive secretary, Dr. Mahesh Chandra, who gave me a very warm welcome as soon as I reached this campus. I must appreciate the efficiency of the staff of Dr. Mahesh Chandra, who are sparing no pains to make our stay comfortable here. And last but not the least, I would like to thank the registrar of the university, IISER Tirupati registrar, for making arrangements for special darshan for me and for several of our fellow colleagues. Now, the title of my lecture is Glimpses of Algebraic Number Theory. The title page shows two institutes. This is Mathematics Department, Punjab University, Chandigarh, where I was groomed, where I was as a student, and did my PhD here, and then worked here till the age of 60, and then I joined IISER Mohali. This is the main gate of IISER Mohali, where I am still affiliated as an INSA honorary scientist, and in Punjab University as an emeritus scientist, Department of Mathematics. This lecture is dedicated to the memory of my great teacher, Professor Ram Prakash Bamba, who departed from us on 26th May 2025. Professor Bamba was a famous mathematician and a very zealous teacher. We were going to celebrate his 100th birthday on 30th of September 2025. We had planned a conference, but that conference was turned into a memorial conference. So Professor Bamba did his FA, B.Ed, MA from Government College Lahore with first position in all exams. In 1946, he joined research at Punjab University, Lahore, under the guidance of an eminent number theorist, Professor Sarvdam Chawla. In a short span of 1 year, Professor Bamba wrote 17 research papers with Professor Chawla. But then partition took place, and Hindus had to leave Lahore, and Professor Chawla shifted to USA. He went to Princeton, and Professor Bamba came to Delhi, and later on Professor Bamba went to Cambridge and worked under Professor L.G. Mordell and got PhD from Cambridge in 1950. Professor Bamba had many awards and honors to his credit. He was a fellow of all the three major science academies of India, as well as a fellow of the World Academy of Sciences, General President of ISCA. He was awarded Ramanujan Medal of INSA, Meghna Saha Award by UGC, Padma Bhushan, and Aryabhatta Medal of INSA. He was Vice Chancellor of Punjab University for 6 years. And he taught me algebraic number theory, the rudiments of algebraic number theory, when I was a PhD student. I didn't do PhD with him, but when I was a PhD student, he taught me a 1 year long course in algebraic number theory, and I was so fascinated by his teaching that I took up algebraic number theory as a subject of my research with some other teacher, Professor Luther. So Pythagorean triples, a triple ABC of natural numbers. Natural numbers means ordinary numbers 1, 2, 3, 4, 5. Satisfying a square plus b square equal to c square is called a Pythagorean triple. That means ABC form the sides of a right angle triangle. There are many Pythagorean triples in view of the following formula: a square minus b square whole square plus 2ab whole square equal to a square plus b square whole square. Substitute different values of a and b and you will get different triples. While studying Pythagorean triples in the famous book Arithmetica by Diophantus of Alexandria in 1637, Pierre de Fermat wrote the following note in the margin of this book. So this was a book, and in the margin of 3 inches margin of this book, Pierre de Fermat, I will tell you who was Pierre de Fermat. He was not a mathematician. He was a judge. He was a lawyer in a court. It is impossible to write a cube as a sum of 2 cubes, a fourth power as a sum of 2 fourth powers, and in general any power beyond the second, because there are infinitely many powers, second powers which can be written, whose sum turns out to be another second power. But it is impossible to write a cube as a sum of 2 cubes, a fourth power as a sum of 2 fourth powers, and in general any power beyond the second as a sum of 2 similar powers. The life of, I must tell you about the life of Pierre de Fermat. That is very inspiring. Fermat was born in 1601 in a town in southwest of France. His father was a wealthy leather merchant, so he was privileged to enjoy education in good schools. But he joined law at Orleans, and pressure from his family steered Fermat towards a career in civil service. Like all Indian parents, his parents wanted him to join civil services. So by 1631, Fermat was a magistrate and a councillor at the Chamber of Petitions at Toulouse. But Fermat did mathematics as a hobby in his leisure time. Yet he contributed a lot toward the advancement of the subject. So you see, mathematics, if it fascinates anyone, he or she can spare time for it. One of the inventors of analytic geometry, Fermat laid technical foundations of differential and integral calculus, and with Pascal he established the conceptual guidelines of the theory of probability. But Fermat is best remembered for his work in number theory, in particular for Fermat's last theorem, which states the following: that the equation x to the power n plus y to the power n equal to z to the power n has no solutions in non-zero integers x, y, z when n is strictly greater than 2. Of course, when n equal to 2, in the beginning we saw that there were many solutions, infinitely many solutions. Fermat himself proved the case n equal to 4 of this theorem. Over the years, Fermat's last theorem was proved for specific values of n. History reveals that in 1770, Leonard Euler used the field Q omega, where omega is a complex cube root of unity, to prove this theorem for n equal to 3. So it was being proved by bits and pieces. Now if n equal to Pm, then the relation x to the power n plus y to the power n equal to z to the power n implies that we write n equal to Pm. So x to the power m to the power p plus, so this is simple school mathematics of 5th class, plus y to the power m to the power p equal to z to the power m to the power p, which gives a solution of the equation x to the power p plus y to the power p equal to z to the power p. Since any integer greater than 2, strictly greater than 2, is either a multiple of 4 or has an odd prime factor, so for proving Fermat's last theorem, it's enough to prove that x to the power p plus y to the power p equal to z to the power p has no solution in non-zero integers for all odd prime exponents p. Because Fermat himself proved that. This celebrated theorem motivated the origin of algebraic number theory, which comes in the title of my lecture. This celebrated theorem motivated the origin of algebraic number theory. Simon Singh, who is a science writer, science fiction writer, he's made many films. Simon Singh, in his book Fermat's Last Theorem, and also written books on the history of science, takes us through a journey of the struggle of the math world for more than 330 years to prove this theorem. So this single result, which Fermat wrote in the margin of Diophantus' book, took more than 330 years to prove the result. So next slide. This is the book written by Simon Singh, and this not only arouses one's interest in mathematics, this arouses one's interest in science. So I think every library should have this book. This is not very expensive. This was declared bestseller. The first major step towards a general proof of Fermat's last theorem was by a French woman, Sophie Germain. You will object to me why I have not called who is the first major step was proved by a French woman. I have not called her a mathematician because she never went to school. She never went to a college. She never went to a university. In her letter dated May 12, 1819, her father used to hide the candles. He used to switch off the heating in her room so that she could not do mathematics. Yet she continued. And when L'École Polytechnic was opened in Paris, women were not allowed to register themselves. So she registered her name for correspondence, for notes under a pseudonym Monsieur Leblanc, Mr. Leblanc. So she registered a wrong name of a woman, and then the course coordinator was none other than Louis Lagrange, and he could not ignore the brilliance of the answer sheets of this woman Sophie Germain. So he sought a meeting with Sophie Germain, and Sophie Germain was compelled to reveal her identity. But then Lagrange introduced her to Gauss, the greatest number theorist of that time. Until now, in the history of number theories, he is called Prince of Mathematicians. So that's how she got introduced to Gauss. So in 1819. In her letter dated May 12, 1819, written to Carl Friedrich Gauss, she explained her idea of the proof. And I will not read the complicated statement she proved, but I will read the simple version of her statement that the equation x to the power p plus y to the power p equal to z to the power p has no solutions in integers x, y, z, with p not dividing any of x, y, z. This is referred to as the first case of Fermat's last theorem. The first case of Fermat's last theorem for the prime p. In particular, she proved that this x to the power p plus y to the power p equal to z has no solution in integers x, y, z, with p not dividing x, y, z if both p and 2p plus 1 were odd primes, like 3 and 7. When p equal to 3, then 2p plus 1 is 7, they are primes. Like 5 and 11. They are both primes. So she proved for all such cases. So this is Sophie Germain, and this is Carl Friedrich Gauss, who turned out to be her mentor later, through writing of letters, never meeting each other. So in this way, she was able to prove the first case of Fermat's last theorem for all primes less than or equal to 197. In 1825, her method claimed its first complete success when the famous mathematicians Peter Gustav Lejeune Dirichlet, this is a French mathematician, and Adrien Marie Legendre, working independently from two different corners of the world, were able to prove the case p equal to 5 of Fermat's last theorem based on Sophie Germain's method. 14 years later, French mathematician Gabriel Lamé proved the case p equal to 7 using Germain's results. Her results related to Fermat's last theorem remained most important until the contribution of German mathematician Edward Kummer in 1847. So we turn to Kummer now. Edward Kummer. So what did he do? We come to it. The German mathematician Edward Kummer contributed a lot towards this subject. Towards this subject means algebraic number theory. The concept of an ideal of a ring was born in the work of Kummer and Dedekind. In 1850, by using the theory of ideals, Kummer proved Fermat's last theorem for a wide range of prime exponents. And number theorists call them regular primes. I will not define what are regular primes. For this great achievement of Kummer, the French Academy of Sciences awarded him its grand prize in 1857. Attempts to prove Fermat's last theorem led to the discovery of algebraic number theory and a wealth of other mathematical discoveries. The theory now has applications to several topics in mathematics. It is this wider link that led to the final complete proof of Fermat's last theorem by Andrew Wiles, by English mathematician Andrew Wiles. So we will I'll tell you the story of Andrew Wiles also. So this is Kumar. And next slide. It's very inspiring. Andrew Wiles' story is very inspiring. In 1963, a 10-year-old boy sitting in the Milton Road Library in Cambridge read the statement of Fermat's last theorem. He was 10 years old. In E.T. Bell's book, The Last Problem. So he was fascinated by this simple looking problem, because it says that x to the power p plus y to the power p equal to z to the power p has no solution in non-zero integers x, y, z when p is a prime strictly greater than 2. P is an odd prime. So he was fascinated by this simple looking problem. Quote, I knew from the moment that I would never let it go. I had to solve it. Unquote. Andrew Wiles revealed when he solved the problem in 1993. After 30 years of dreaming and 7 years of single-minded efforts, Wiles completed a proof of Fermat's last theorem by May 1993. He outlined the proof in 3 lectures in a conference held at Sir Isaac Newton Institute in Cambridge, which was his alma mater. He did his PhD from Cambridge, and later he went to Princeton for a job in June 1993. The title of Wiles' lecture, I will not read the title because this is meant for mathematicians. At the end of his 3rd lecture on June 23, 1993, when he concluded the proof of Fermat's last theorem, he became the most famous mathematician in the world. The TV channels, the newspapers, every front page of this was covered with this news that Andrew Wiles has proved the Fermat's last theorem. So this is Andrew Wiles. This is how he looks now. At that time he was much younger. In the words of Cambridge Professor John Coates, who was PhD supervisor of Andrew Wiles, quote, a proof of Fermat's last theorem is a great intellectual triumph, and one should not lose sight of the fact that it has revolutionized number theory in one fell swoop. For me, the charm and beauty of Andrew's work is that it has been a tremendous step for algebraic number theory, unquote. So these are the words he said, his supervisor, PhD supervisor said. So, so what are algebraic numbers after? Algebraic numbers, all of you know rational numbers are a over b, where a and b are integers. And what are algebraic numbers? A complex number alpha is said to be an algebraic number if it's a root of some non-zero polynomial with coefficients from the field Q of rational numbers. This makes sense for those who have read something like BSc in mathematics. A subfield of complex numbers having finite dimension as a vector space over Q is called an algebraic number field. An algebraic number alpha is said to be an algebraic integer if it is the root of some monic polynomial with coefficients from the set Z of integers. Algebraic number fields of degree 2, 3, 4, 5, 6 are respectively called quadratic, cubic, quartic, quinatic, sextic fields. Of course, there are names beyond that, but I will speak only up to sextic fields in this lecture. Now, there is something called notion of an integral basis meant to, again for mathematicians. My non-mathematician friends should excuse me for this, because I have to tell something about my work also. Very little, very little. So if K is an algebraic number field, then degree of the extension K over Q is called the degree of K. The set of all algebraic integers of K is usually denoted by AK, and the properties of AK are: AK is an integrally closed domain with quotient field K. AK is a free module, a free abelian group of rank equal to the degree of K over Q. Any Z basis of AK is called an integral basis of K. That is a subset W1, W2, Wn of AK is an integral basis of K if every element of AK can be uniquely written as a linear combination of W1, W2, Wn with coefficients from Z. A quadratic field K equal to Q root D with D square for integer has integral basis 1, W. This is the first result which we teach in the first chapter of algebraic number theory, with W equal to 1 plus under root D by 2 or under root D according as D is common to 1 mod 4 or not. So then there is a very important notion which we also teach in the second chapter, discriminant of an algebraic number field. If W1, W2, Wn is an integral basis of an algebraic number field K, then the determinant of the n cross n matrix having ijth entry trace Wi, Wj, this is called the discriminant of k, and it will usually denoted by dk. So if k equal to q theta with theta in ak having minimal polynomial fx of degree n over q, and if theta 1, theta 2, theta n are the roots of fx, then the discriminant of fx, the discriminant of the polynomial fx is defined by this. And the discriminant of fx and the discriminant of k are related by the formula discriminant fx is index of z theta in ak whole square, index of the subgroup z theta in ak whole square multiplied by the discriminant of k. Next slide. So basic properties of discriminant of number fields, Ludwig Stickelberger proved in 1897 that discriminant of an algebraic number field is always congruent to 0 or 1 mod 4. That's an integer. When you divide it by 4, the remainder is always 0 or 1. An embedding of an algebraic number field K is a homomorphism sigma from K into C. It's called real if the image is contained in reals, and otherwise it is called non-real. And Brill proved a theorem regarding the sign of the discriminant. The sign of the discriminant is same as minus 1 raised by R2, where R2 is the number of 2R2 is the number of non-real embeddings of K. And such an algebraic number field is said to have signature R1, R2. If it has real, R1 real isomorphism and 2 R2 non-real isomorphisms, because non-real isomorphisms occur in conjugate pairs. So, and Hermite proved in 1857 only a finite number of algebraic number fields can have the same discriminant, and Hermite's theorem led to the search for finding the number of those number fields, specifically finding those number fields with given signature R1 and R2 whose discriminant is smallest in absolute value. Such smallest value of the discriminant is noted by M R1 R2, and it can be, of course, these little things we prove in our first course in algebraic number 3. M20 is 5, M01 is 3, M11 is 23, realized by k equal to q alpha, alpha q equal to 1 plus alpha. M30 is 49, and it's realized by k equal to q beta, where beta satisfies this relation. It may be pointed out that M60 was determined by Gurnam Kaur in her PhD thesis in 1964 under the supervision of Professor Bamba at Punjab University, Chandigarh. So now by pure number field of degree n, and we mean an algebraic number field k equal to q theta, where theta is the root of an irreducible polynomial x to the power n minus a over z. And in 1900, Richard Dedekind was the first to describe an integral basis of pure cubic fields and pure prime degree number fields. Their discriminant was found by Westerlund, and this problem for quadratic fields was solved by Funakara in 1984, and for general n with some restriction, with some relation between a and n, it was solved by my students Jhakhar and Khanduja, Jhakhar and Sangwan jointly with me in 2021. So next slide. To find a formula for the construct an integral basis for general pure fields of degree, and this problem has been solved by Anu Jhakhar, one of students who did PhD with me, for pure sextic fields in 2021, and for pure fields of degree PQ, where P and Q are distinct primes, in 2022. A formula for the discriminant with the method to compute an integral basis of each cubic field was given by Swan and Raka in 1998. The same problem has been solved for all those quadratic and cunic fields which are generated over Q by root of an irreducible trinomial of the type x to the power n plus ax plus b belonging to zx for when n equal to 4 or 5 by Alaka and Williams in 2004. In 2022, this problem was solved for sextic fields by my student Sumandeep Kaur jointly with me for general, and the problem is still open. And this is Anuj Jhakhar, who is a faculty at IIT Madras, and this is Neeraj Sangwan, and this is Sumandeep Kaur. Next slide. Discriminant of number fields defined by exponential Taylor polynomials. This result is proved by by one of my students, Ankita Jindal, who she didn't do PhD with me. She only studied in MSc from me. Let P be a prime number and let n greater than 2 be an integer having periodic expansion C1 p to the power m1 plus C2 p raised by m2 plus Cs p raised by ms, where mi's are strictly increasing and m1 may be 0, but Ci's are all positive and lying between 1 to p minus 1. Let k equal to q theta be an algebraic number field with theta a root of the famous irreducible polynomial whose irreducibility was proved by Schur in 1929. Fn x equal to x to the power n factorial over n minus 1 factorial. It is x to the power n plus x raised by n minus x to the power n over n factorial plus x raised by n minus 1 over n minus 1 factorial plus 1 plus x square over 2 factorial plus x over 1 factorial plus 1 whole multiplied by n factorial. So let dk stand for the discriminator of k and di for the integer p raised by mi minus 1 over p minus 1. Then the highest power vp dk of p dividing dk is given by this simple formula in 2025. So next slide. Ankita Jindal, she of course she did MSc from Punjab University long time back, but then we met at a workshop where I was a resource person, she was a tutor, and then we conceived this problem while we were visiting Indian National Army War Museum in Moirang in Manipur, and this Moirang is a place where Indian flag was hosted first time after independence of India. So we did that, and my constant source of inspiration has been my parents, Sardarni and Sardar Kesar Singh, who are no more, and my tower of strength has been in this journey my family, consisting of my 2 sons, daughter-in-laws, and my grandchildren. Then my source of strength, of course, has been my PhD students. And one of them is absent because she died a long time back, my PhD students. She was older than me, and all these are have been my PhD students. And these are the references arranged in a chronological order. Next slide. And this is the latest paper about which I have talked with Ankita, and thank you very much.
Thank you, Dr. Khanduja. Any quick questions? Okay, I think there is no other question. So I have to thank all the speakers in this session.